Hi everybody and welcome to another video of the Optimization Masterclass. So this class is going to be based on the course that I do at Imperial College, which is based on this book, Convex Optimization, of Stephen Boyd and Lieven Vandenberger. If you haven't followed the previous lectures in this series, please check the link over here. Remember that you can download the material that I use to teach the class, so the so-called smart handouts, from the link in the description down below. If you have suggestions on future topics that you would like that I cover in this masterclass, please leave it in the comments below. Thank you very much and enjoy the course. Let's now look at another class of problems which belongs to the group of approximation and estimation problems, which is regularized approximation. And in a way, regularized approximation puts together the previous two problems, okay? So here the problem is essentially to find a vector x which is small and also makes the residual ax minus b small. Okay, so this is the first example in this course of a multi-objective optimization problem. So we want to minimize two different objectives, okay? And the two norms can be different in general, can be penalty functions, can be different penalty functions, okay? So this problem is obviously a variation of the least norm problem, okay? What is the difference between the least norm problem and this problem that we have here? Well, the main difference is that before we needed to satisfy the constraints exactly. We really needed that the residual ax minus b is 0. That's was before. Now we don't care that it's 0. It has to be small, depending on the penalty function that we use, but we are happy to trade some non-zero residuals in ax minus b as long as we get a small x. Okay, so it's different. It's a different problem. Okay, we are looking for a different objective. Now, we will cover in detail multi-objective optimization problems later on in the course. The reason why we cannot cover it now is because we require some mathematical theory, which I'm not introducing at the moment. So I just want to give some general idea about what a multi-objective optimization problem is and the properties of it. But again, keep in mind that we will cover this later in detail. So in a multi-objective optimization problem, we don't have a classical optimal solution because essentially a solution depends on how much we care about one objective with respect to the other. If we care a lot about the first objective with respect to the second, we get an optimal solution. But if instead we care more about the second objective rather than the first, the optimal solution will be different. It's still an optimal solution for essentially a different problem. So this is to say that essentially the standard concept of optimal solution doesn't work in multi-objective optimization problem, and there is going to be a trade-off between the objective, the first objective and the second objective. An optimal point, an optimal solution for an instance of this problem is called a Pareto optimal point. And since by trading off between one objective and the other objective, we obtain different optimal points, we essentially get a curve of optimal points, and this is called Pareto optimal curve. Okay, this is just to give you an idea of the fact that the multi-objective problems are a bit more complicated than standard problems because the standard idea of optimal solution, it doesn't really make sense. But we will study this in detail later on. For the moment, you just have to think that a multi-objective problem is a problem in which the solution depends on how much we care about one objective with respect to the other. And if you change, how much you care about one with respect to the other, the solution will change. The optimal solution will change. One way to solve a multi-objective optimization problem is by summing the two objectives and multiplying one of the two by a constant. And you see that if this constant gamma is 0, then that means that we care just about the first objective. If gamma is infinity, then we care just about the second objective. By changing gamma, we're changing how much we care about one objective with respect to the second objective. This type of formulation in 8, this type of optimization problem, it's a type of optimization problem that is commonly called regularization. And actually, it will make sense soon, later on. I mean, I will explain it soon why this is called regularization. But the point is this, I mean, by varying gamma, you get different trade-off between the two objectives. Regularization is used in in a lot of different contexts. As we said, we may think about the fact that we want to minimize the residuals, but then we also want to penalize large values of x. Okay, so that's a possible application of in which regularization and this formulation may make sense. This formulation in 8 can be also, for instance, can arise also in other applications in which we have again a model which is a times x, which is just an approximation, a linear approximation of an underlying more complex model, which is actually f of x. Then we know that this linearized model makes sense only for small values of x, and that's why we don't want just to minimize the objective ax minus b, but we also care about obtaining small x. Okay. And of course, we can think about other cases in which this, the regularization problem comes out. But generally speaking, the idea here is simply that we want to we want to have small residuals, but we also want to have small x. One very popular type of regularization is the Tikhonov regularization, which is also called rich regression. I'm sure that you have seen it in some machine learning classes. It's a very, a basic type of cost function and in particular of regression. And that happens when essentially the two norms that we are using are squared Euclidean norms. This problem, as usual, when we use L2 norms, can be solved exactly. I leave it as an exercise to solve it. This is an unconstrained optimization problem, which is smooth, so you compute the gradient, you set the gradient equal to 0, you find the solution. Once you find the solution, what you notice is that the solution has this form here, in which you have to compute the inverse of A transpose A plus gamma I. And this matrix has the property that for any gamma greater than 0, this matrix is going to be invertible. So essentially, the way in which Tikhonov regularization can be thought of is that you start with a problem which is singular. So you have a matrix A which is singular, and you want to regularize that. And Tikhonov regularization allows you essentially to add a small gamma to your matrix A, which allows you to compute the inverse and so to find the solution. Another way to look at this problem is you want to solve the equation ax equal to b, but the equation is singular, and so that is going to give you, or maybe not singular, but it's badly conditioned. Okay, so that means that it's not singular, but it's close to singularity. And if you compute the solution, you're going to get a huge x. And then by using Tikhonov regularization, you are waiting, you want to have a small x in norm, and that's going to essentially give you a solution which is a trade-off between the solution of ax minus b and your a big x. More generally, Tikhonov regularization can be used for other formulations. For instance, it can be used to obtain a smooth solution. So instead of waiting x, so instead of asking for small x, we can ask for minimizing this objective delta x, which indicates an approximation of the second derivative, for instance. Okay, this is just a symbol here. So the idea here is that we can weigh the second derivative, and this will make the solution to have little variation, okay, not fast variations, and that's going to smooth our solution, okay, so it's going to have small curvature. So this is to say that Tikhonov regularization doesn't have necessarily to be used together with x. It can be used also with a function of x. Okay, let's look at a concrete example. Okay, so let's assume that we have a discrete time dynamical system, okay, in which we have an input sequence u and then an output sequence of y's. This is nothing else than the impulse response of the system. Okay, so our goal is to design the input, and we want to design the input achieving certain multiple objectives. So for instance, the first objective that we want to achieve is tracking. We have a certain signal, like for instance a profile that we want to track. So our device has to track a certain profile. For instance, think about a circuit, and you want to track a certain waveform in your circuit, and you want to design the input in such a way that your circuit is going to track that waveform. How do we do that? Well, we want to definitely weight the difference between, for each instant of time, the difference between your output and the desired output, and we weight this using an L2 norm, okay? But we don't want to do just that. We also want to minimize the energy that we use to achieve this objective. And so this means that we want to minimize the square of U. Maybe in addition to that, we know also that our device cannot really change input very quickly. There is some limitation, physical limitation. This can be the case, for instance, if our device is mechanical. You know, if it's a mechanical device, the parts in the mechanical device cannot change suddenly. Okay, it takes a bit of time to actually, have things rotating and moving. So we don't want to have large values of large variation of our input, because even if in theory it works, in practice it cannot be realized. And so in that case we want to limit the variation between the value of the input at k and the value of the input at k plus 1. And again we take an L2 norm to weight this. So in total our minimization problem is going to be the problem of minimizing the sum of these three objectives, and of course we are weighting these three objectives with certain constants depending on how much we care about each objective. We do a simulation and we have three results. Okay, so let me zoom out so that we can see them better. So we have three results in which this column here, okay, so this the left column represents the inputs, the optimal input U that we found with our optimization, solving our optimization problem, and the right plots represents the produced output Y. Okay, so what we want to follow, to track, is a square wave. So the dashed line here, which is visible here but is not visible there but is there as well, is our signal that we want to track. So the first solution is given when essentially in our problem both delta is going to be 0 and eta is going to be small. Okay, so we don't care about big magnitude of the input, we don't care about variation of the input, we just care about tracking. So the solution is going to track very, very well, but we see that there are big spikes and there is a lot of variation in the oscillation in the input. So then the next things that we're going to consider is the case in which we still have delta equal to 0, but we have a large, not a large, maybe let me check one more. Yeah, we have a larger eta, okay? So that means that now in the second plot, we care about not having a too big magnitude. And you see that now the magnitude is decreased. You see that this peak was around 5 and now it's around 2. This peak was around 8 and now it's around, -8 and now it's around -4, okay? The result, however, is that the tracking gets worse, but the output Y is more smooth, okay? Finally, the third plot is when we both have a big eta and a non-zero delta, so we are penalizing variation, and then we see that okay, the input value is never too big and there is no oscillation anymore. Okay, so the input profile is very smooth. And actually the result is quite good because it's essentially the same as before, so the tracking is not perfect, but it's okay, it's acceptable, and there is no oscillation anymore. Okay, so this is an example, I mean, to show you how you can weight multiple criteria at the same time, multiple objectives at the same time, and by varying these parameters, you get different solutions, different optimal solutions. And it really depends what you care about. If you care about tracking the most, then you will look for this. If you don't care too much about the tracking, but you care more about smoothness, then you look for the solution, third solution. The second doesn't really make sense in this case. I mean, it's not really doesn't give you a good improvement with respect to the last one, for instance. Let's look at a different example. So in this example, we have an audio signal xi, which is sampled at time I, okay? But unfortunately, when we sample this signal, we introduce a certain error, okay? So what we actually measure is this X core, okay, which is the sample signal with some noise, small noise V. Okay, this noise is small in amplitude, but is high frequency. Okay, so it's an additive high frequency noise. What we would like to do is essentially, given the corrupted signal X core corrupted, we want to reconstruct the original signal X. This problem is called signal reconstruction, or denoising, or smoothing. So here the idea is that we want to achieve two things. The first thing is that we want to find the best X, which essentially is close to our X corrupted, okay? But then we also want to regularize our estimated X, because we know that, I mean, we don't know anything about the real X. We have just X corrupted, and so what we want is to get an X which is close to X corrupted. But we know that X corrupted is corrupted by a high frequency noise. That means that the X that we want to find, well, we want to filter it. We want to have, not a high frequency signal. So we want to smooth out the high frequency components, okay? So one way to do that is that we can do some smoothing through this phi, okay? And to do this smoothing, I mean, we look at two different smoothing. One is a quadratic smoothing, which is essentially done by computing the L2 norm of the differences between the signal at this instant of time I and the signal at the next instant of time I. And the other smoothing that we look at is the total variation smoothing, okay? In which essentially we compute the L1 norm of the differences in this case, okay? What do we get? Well, let's look at a simulation. What we have here, this plot, is the original signal that we would like to estimate, and this is the corrupted signal with some high frequency noise. And now here we have three cases for the quadratic smoothing and three cases for the total variation smoothing. So let's first look at the quadratic smoothing. Essentially what we do here is we go from a high smoothing to a low smoothing. So essentially we decrease the weight of the second objective, okay? So we decrease the gamma essentially as we go down over here. What we get is we get a better profile for the original signal, which is essentially which is discontinuous, but we also get back the high frequency. And if we want to get rid of the high frequency, then we get smooth signal over here, which is bad. I mean, the original signal has this discontinuity. It's like if you essentially have a signal in which you have, like a drum noise, like a bum, bum, bum. So very, very sharp. But if we use this denoising, well, that's going to be smooth quite a lot, and the audio is going to be deformed quite a lot. Otherwise, we can have it sharp, but we're going to still have some high frequency noise. The total variation smoothing instead works very well because you see that, again, as we go down, we decrease the smoothing. And as we see that we still preserve this discontinuity signal, okay, the discontinuity property, so that the sharp noise is still going to be a sharp noise, even if, for instance, the high frequency noise is not too bad, okay? So it looks like that for this application, total variation smoothing makes more sense than the usual quadratic smoothing. And the last thing that I want to say is that, I mean, Tikhonov regularization is not the only type of regularization that is used. There are other common regularization techniques, and for instance, another one that is common is one in which we weight with an Euclidean norm the residuals, and we use a L1 norm for X. Of course, we can already imagine what this is going to produce. Well, it's going to produce a solution with which is going to reduce the residuals, and among the solution that is trying to solve this AX minus B, we look for the one which is sparse, because we know that the L1 norm produces a sparse solution.